categories of breast cancer showing different gene expression. So we see here is a heat map of the full data, 88 women in the columns and about 8,000 genes in the rows. And hierarchical clustering, which we'll discuss in the last part of this course, has been applied to the columns, and you see the clustering tree at the top here, which has been expanded for your view at the top. And hierarchical clustering has been used to divide these women into roughly 6 subgroups based on their gene expression.
It's very effective, especially with these colors. You can just see these clusters standing out.
Yeah. Hierarchical clustering and heat maps actually have been a very important contribution for genomics, which this is an example of, simply because they enable you to see and to organize the full set of data on just in a single picture. And the bottom right here is some more, we've drilled down to look more at the gene expression. Like, for example, this subgroup here, these red patients seem to be high largely in these genes and maybe in these genes. So we'll talk about this example in detail later on in the course.
Establish the relationship between salary and demographic variables in population survey data. So here's some survey data. We see income from the Central Atlantic region of the USA in 2009. And you see what you might expect to see as a function of age. Income initially goes up, then levels off, and then finally goes down as people get older. Incomes gradually increase with year as the cost of living increases, and incomes change with education level. That's the right-hand plot. Those are box plots. And so here we see the three of the variables that affect income. And again, the goal is we use regression models to try and understand the roles of these variables together and see if there's interactions and so on.
And our last example is Landsat images of land use area in Australia. So this is a rural area of Australia.
Those are harsh colors, Rob. Did you choose those colors?
You probably did, Trevor. You're the color.
This is before I developed taste.
When did that happen? I didn't see the news memo. Okay, so here are these are from Landsat images. So let's start here in this panel. So this is again a rural area of Australia where the land use has been labeled, I think actually by graduate students or researchers into one of 1, 2, 3, 4, 5, 6.
They don't have to pay their graduate students as much as we do.
So they've been labeled, and these colors are indicating the different labels. These are the true labels. And the goal is to try to predict these true labels from the spectral bands at 4 frequencies taken from a satellite image. And so here's the power at the different frequencies in 4 spectral bands. So we have features which are, now they're pretty complicated because we have features, spatial features, 4 layers of them, and we're going to try to use those combination of features to predict the land use that we see here. And
pixel by pixel, right?
Pixel by pixel.
Yeah.
Although we might want to use the fact that nearby pixels are more likely to be the same land use than ones that are far away. And we'll talk about classifiers. I think the one we use here is actually nearest neighbor. It's a very simple classifier, and that produces the prediction in the bottom right. And you can see it's quite good. It's not perfect. There's a few mistakes it makes, but it's for the most part quite accurate.
Okay, so that's the end of the series of examples. In the next session, we'll just tell you some notation and how we set up problems for supervised learning, which we'll use for the rest of the course.
Well, here we are again, 8 years later. I'm Trevor Hasty, and this is my friend Rob Tipsharani.
Thank you, my old buddy Trevor. Well, may I say, you haven't changed one bit. You look great.
Oh, thank you, Rob.
Well, we're here filming the second edition of our MOOC lectures on our course,
Introduction to Statistical Learning.
Statistical Learning. You can take your costume off now.
It's off, Rob.
Oh, okay, sorry. So, welcome to the second edition of our lectures on statistical learning. We have some new lectures to accompany the new edition of our book. And the new lectures will be on deep learning,
survival analysis, and multiple testing, as long as a few other topics. In addition, you'll notice if you look in the book, which is also freely available on our websites and on the book website, you'll notice there's a few little extra pieces in various chapters. So in chapter 4, we have a new section on generalized linear models. In the unsupervised learning chapter, we have a section on matrix completion. And there's one more. BART, in the tree chapter, Bayesian additive regression models, BART. The rest of the course is the same as before, so we haven't reformed those lectures. The material is the same. And of course, there's labs for the new material as well. So we hope you enjoy it. In addition, in the first edition of the course, we had interviews with some famous people in our field. Well, we have more of those. Right, we've interviewed David Cox on survival analysis, Jeff Hinton on deep learning, and Yoav Benjamini on multiple testing and false discovery rates. So we hope you enjoy the second edition of the course.
Third edition.
I like your new haircut, Rob. Makes you look years younger.
Trevor, I think you need to better put on your glasses.
Welcome, Jonathan Taylor, to the Statistical Learning team. The Statistical Learning edX course was developed by Rob Tipsharani and myself in 2014, with an updated edition in 2021. The course explains the concepts of statistical learning, and it is based on our book, co-authored with Gareth James and Daniela Witten, called An Introduction to Statistical Learning with Applications in R. The second edition was published in 2021. Here we present a new course, Statistical Learning with Python, along with our new co-author and Python expert, Jonathan Taylor.
Thank you, Trevor. The course is based on our new book, An Introduction to Statistical Learning with Applications in Python. In the course and in the book, all the labs at the end of each chapter are implemented in Python. We provide Jupyter Python notebooks, as well as the Python package ISLP. The package contains all the datasets used in the book, along with many new and useful tools for statistical modeling.
Wowzers, Jonathan. I'm so excited about this book.
Oof, wowzers. That's a bit sus, Trevor. I think that goes back to the 80s.
Oof, you're right. Yeet! Great to have you on board, Jonathan. Jonathan is an early Python adopter and has made many contributions to the community.
Like the earlier book, the PDF of this book is available for free from the Stat Learning website, along with Python resources. We hope you enjoy the class.
Honor code. Supervise. No.
Okay, now we're going to talk about the supervised learning problem and set down a little bit of notation. So we'll have an outcome measurement y, which goes by various names, dependent, variable, response, or target. And then we'll have a vector of p predictor measurements, which we usually call x. They go by the name inputs, regressors, covariates, features, or independent variables. And we distinguish two cases. One is a regression problem. Y is quantitative. such as price or blood pressure. In the classification problem, y takes values in a finite unordered set, such as survived or died, the digit class is 0 to 9, the cancer class of the tissue sample. Now we have training data pairs, x1, y1, x2, y2 up to xn, yn. Now again, x1 is a vector of p measurements, y1 is usually a single response variable. And so these are examples or instances of these measurements. So the objectives of supervised learning is as follows. On the basis of the training data, we would like to accurately predict unseen test cases, understand which inputs affect the outcome and how, and also to assess the quality of our predictions and the inferences.
So, by way of philosophy, as you take this course, we want not just to give you a laundry list of methods, but we want you to know that it's important to understand the ideas behind the various techniques so you know where and when to use them. Because in your own work, you're going to have problems that we've never seen before, you've never seen before, and you want to be able to judge which methods are likely to work well and which ones are not likely to work well. As well, not just prediction accuracy is important, but it's important to try simple methods first in order to grasp the more sophisticated ones.
We're going to spend quite a bit of time on linear models, linear regression, and linear logistic regression. These are simple methods, but they're very effective.
And it's also important to understand how well a method is doing. Right? It's easy to apply an algorithm, and nowadays you can just run software, but it's difficult, but also very important to figure out how well is the method actually working. So you can tell your boss or your collaborator that when you apply this method we've developed, this is how well you're likely to do tomorrow. And in some cases you won't do well enough to actually use the method, and you'll have to improve your algorithm or maybe collect better data. The other thing we want to convey just through the course and hopefully through examples is that this is a really exciting area in research. I mean, statistics in general is a very hot area. Statistical learning and machine learning is of more and more importance, and it's really exciting. The area is not gelled in any way in the sense that there's a lot of good methods out there, but a lot of challenging problems that aren't solved. So,
especially in recent years, right, with the onset of big data and coined the word data science.
Right, and statistical learning, as Trevor mentioned, is a fundamental ingredient in this new area of data science. So you might be wondering where does the term supervised learning come from? It's actually a very clever term. I like to take credit for it, but I can't. It was developed by someone in the machine learning area. The idea of supervised learning, think in the kindergarten of a teacher trying to teach a child to classify, to discriminate between what a house is and a bike. So he might show the child, maybe Johnny, say, Johnny, here's some examples of what a house looks like, and maybe in Lego blocks, and here's some examples of what a bike looks like. So he tells Johnny this and shows him examples of each of the classes, and the child then learns, oh, I see, a house has got sort of square edges, and a bike has got some more rounded edges, etc. That's supervised learning because he's been given examples of labeled training observations. He's been supervised. And as Trevor just sketched out on the previous slide, the Y there is given, and the child tries to learn to classify the two objects based on the features, the X's. Now, unsupervised learning is another topic of this course. In which I grew up. See, that's the problem. Okay. Well, so in unsupervised learning, now in the kindergarten, now Trevor's in kindergarten, and Trevor was not given examples of what a house and a bike was. He just sees on the ground lots of things, right? He sees maybe some houses, some bikes, some other things. And so this data is unlabeled. There's no why.
Oh, it's pretty sharp, right?
Okay. So the problem there now is for the child it's unsupervised to try to organize in his own mind the common patterns of what he sees, right? He may look at the object and say, oh, these three things are probably houses, or they're not called houses, but they're similar to each other because they have common features. These other objects, maybe they're bikes or other things, they're similar to each other because I see some commonality. And that brings the idea of trying to group observations by similarity of features, which is going to be a major topic of this course, unsupervised learning. So more formally, again, there's no outcome variable measured, just a set of predictors. And the objective is more fuzzy. It's not to predict y because there is no y. It's rather to learn about how the data is organized and to find which features are important for the organization of the data. So we'll talk about clustering and principal components, which are important techniques for unsupervised learning. One of the other challenges is it's hard to know how well you're doing. Right? There's no gold standard. There's no y. So when you've done a clustering analysis, you don't really know how well you've done. And that's one of the challenges. But nonetheless, it's an extremely important area, both because, one reason is that the idea of unsupervised learning is an important preprocessor for supervised learning. It's often useful to try to organize your features, choose features based on the X's themselves, and then use those processed or chosen features as input into supervised learning. And the last point is that it's a lot easier, it's a lot more common to collect data which is unlabeled, right? Because on the web, for example, if you look at movie reviews, a computer algorithm can just scan the web and grab reviews. Figuring out whether the review, on the other hand, is positive or negative often takes human intervention. So it's much harder and costly to label data, much easier just to collect unsupervised, unlabeled data.
Well, the last example we're going to show you is a wonderful example. It's the Netflix prize. Netflix is a movie rental company in the US, and now you can get the movies online. They used to be DVDs that were mailed out. And Netflix set up a competition to try and improve on their recommender system. So they created a data set with 400,000 Netflix customers and 18,000 movies, and each of these customers had rated, on average, around 200 movies each. So each customer had not seen, only seen about 1% of the movies. And so you can think of this as having a very big matrix, which is very sparsely populated with ratings between 1 and 5. And then the goal is to try and predict, as in all recommender systems, to predict what the customers would think of the other movies based on what they rated so far. So Netflix set up a competition where they offered a $1 million prize for the first team that could improve on their rating system by 10% by some measure.
And the design of the competition was very clever. I don't know if it was by luck or not, but the root mean square error of the original algorithm was about 9.953, so that's on a scale of 1 to 5. And it took the community, when they announced the competition and put the data on the web, it took the community about a month or so to have an algorithm which improved upon that. But then it took the community about another 3 years for someone to win the competition.
So it's a great example. Here's the leaderboard. At the time the competition ended, it was eventually won by a team called Bellcore's Pragmatic Chaos. But a very close second was Ensemble. In fact, they had the same score up to 4 decimal points, and the final winner was determined by who submitted their final prediction. Predictions first. So it was a wonderful competition, but what was especially wonderful was the amount of research that it generated. There were tens of thousands of teams all over the world entered this competition over the period of 3 years, and a whole lot of new techniques were invented in the process. A lot of the winning techniques ended up using a form of principal components in the presence of missing data.
Now, how come our name's not on that list, Trevor? Where's our team?
That's a good point, Rob. The page isn't long enough. I think if we went down a few hundred, you might.
Well, so actually, seriously, we actually tried with a graduate student when the competition started. We spent about 3 or 4 months trying to win the competition. And one of the problems was computation. The data was so big and our computers were not fast enough that just to try things out took too long. And we realized that the graduate student was probably not going to succeed, and he was probably going to waste 3 years of his graduate program, which is not a good idea for his career. So we basically abandoned ship early on. So I mentioned in the beginning the idea of the field of machine learning, which actually led to the statistical learning area, which we're talking about in this course. And machine learning itself arose as a subfield of artificial intelligence, especially with the advent of neural networks in the 80s. So it's natural to wonder what's the relationship. So I mentioned in the beginning the idea of the field of machine learning, which actually led to the statistical learning area, which we're talking about in this course. And machine learning itself arose as a subfield of artificial intelligence, especially with the advent of neural networks in the 80s. So it's natural to wonder what's the relationship between statistical learning and machine learning. And first of all, the question is hard to answer. We ask that question often. There's a lot of overlap. Machine learning tends to work at larger scales. They tend to work on bigger problems. Although, again, the gap tends to be closing because fast computers now are becoming much cheaper. Machine learning worries more about pure prediction and how well things predict. Statistical learning also worries about prediction, but also about models. It tries to come up with models, methods that can be interpreted by scientists and others. And also, machine learning worries more about pure prediction and how well things predict. Statistical learning also worries about prediction, but also about models. It tries to come up with models, methods that can be interpreted by scientists and others. And also, by how well the method is doing. We worry more about precision and uncertainty. But again, the distinctions become more and more blurred, and there's a lot of cross-fertilization between the methods. Machine learning clearly has the upper hand in marketing. They tend to get much bigger grants, and their conferences are much nicer places, but we're trying to change that, starting with this course.
So here's the course text, Introduction to Statistical Learning. We're very excited. This is a new book by 2 of our graduate students, past graduate students, Gareth James and Daniela Wood.
Interpretability.
Britain, and Rob and myself, book just came out in August 2013, and this course will cover this book in its entirety. The book has, as at the end of each chapter, there's examples run through in the R computing language, and we do sessions on R, and so when you do this course, you'll actually learn to use R as well. R is a wonderful environment, it's free, and it's a really nice way of doing data analysis. You see there's a second book there, which is our more advanced textbook, Elements of Statistical Learning. That's been around for a while. That would be serve as a reference book for this course for people who want to understand some of the techniques in more detail. Now, the nice thing is, this course, not only is this course free, but these books are free as well. The Elements of Statistical Learning has been free, and the PDFs available on our websites. This new book is going to be free beginning of January when the course begins. And that's with agreement with the publishers.
But if you want to buy the book, that's okay too. It's nice having the hard copy. But if you want, the PDF is available.
So we hope you enjoy the rest of the class.
就这样吗？没了。Which of the following are supervisory important? Shit. Which one? Predict whether a website user. What? Find genes. Responses are supervised. Okay. Why? True or false? Do you want to go over any or any? Okay. False. Most of them can be framed only. They are predicting and primarily understanding how the input of system drive the output. Chooses the extremely complicated black box and pure function not very useful in and of itself. Size.跟我想不太一样。Supervise learning study， 对啊 ，supervise。Predict very accurate， 不是有吗？为什么？哦 ，Only Go， 干没看到。这种 problem with clearly defined predictors. measurements, predictor. Okay. Congratulations. Introduction to regression models. 我是不是要下载这个 PPT 啊？
Okay, we're going to talk about statistical learning and models now. I'm going to tell you what models are good for, how we use them, and what are some of the issues involved. Okay, so we see three plots in front of us. These are sales figures from a marketing campaign as a function of the amount spent on TV ads, radio ads, and newspaper ads. And you can see at least in the first two, there's a somewhat of a trend, and in fact we've summarized the trend by a little linear regression line in each. And so we see that there's some relationship. The first two again look stronger than the third. Now in a
lecture slides. « 这也太多了吧！fail？ 为什么会 fail？ 哪里啊？ 那么奇怪。哦，按错。为什么找不到啊？呀，上厕所。
Now, in a situation like this, we typically like to know the joint relationship between response sales and all three of these together. We want to understand how they operate together to influence sales. So you can think of that as wanting to model sales as a function of TV, radio, and newspaper all jointly together. So how do we do that? So before we get into the details, let's set up some notation. So yes, sales is the response or the target that we wish to predict or model, and we usually refer to it as Y. We use the letter Y to refer to it. TV is one of the features or inputs or predictors, and we'll call it X1. Likewise, radio is X2 and so on. So in this case, we've got three predictors, and we can refer to them collectively by a vector as X equal with three components, X1, X2, and X3. And vectors we generally think of as column vectors. And so that's a little bit of notation. And so now in this more compact notation, we can write our model as Y equals function of X plus error. Okay? And this error is just a catch-all it captures the measurement errors maybe in Y and other discrepancies. Our function of X is never going to model Y perfectly, so there's going to be a lot of things we can't capture with the function, and that's caught up in the error. And again, f of x here is now a function of this vector x, which has these three arguments, three components. So what is the function f of x good for? So with a good f, we can make predictions of y at new points, x equals little x. So this notation, capital X equals little x, capital X we think is the variable having these three components, and little x is an instance, also with three components, particular values for newspaper, radio, and TV. With the model, we can understand which components of X, in general, it will have P components, if there's P predictors, are important to explaining Y, and which are irrelevant. For example, if we model in income as a function of demographic variables, seniority and years of education might have a big impact on income, but marital status typically does not, and we'd like our model to be able to tell us that. And depending on the complexity of F, we may be able to understand how each component xj affects Y in what particular fashion it affects Y. So models have many uses, and those are amongst them. Okay, well, what is this function f? And is there an ideal f? So in the plot, we've got a large sample of points from a population. There's just a single x in this case and a response y. And you can see it's a scatter plot, so we see there's a lot of points. There's 2,000 points here. Let's think of this as actually the whole population, or rather as a representation of a very large population. And so now let's think of what a good function f might be. And let's say, not just the whole function, but let's think what value would we like f to have at, say, the value of x equals 4. So at this point over here. Right? We want to query f at all values of x, but we're wondering what it should be at the value 4. So you'll notice that at the x equals 4, there's many values of y. But a function can only take on one value. The function is going to deliver back one value. So what is a good value? Well, one good value is to deliver back the average values of those y's who have x equal to 4. And that we write in this sort of mathy notation over here. It says the function at the value 4 is the expected value of y given x equals 4. And that expected value is just a fancy word for average. It's actually a conditional average given x equals 4. Since we can only deliver one value of the function at x equals 4, the average seems like a good value. And if we do that at each value of x, so at every single value of x, we deliver back the average of the y's that have that value of x. So for example, at x equals 5, again, we want to have the average value in this little conditional slice here. That will trace out this little red curve that we have here. and that's called the regression function. So the regression function gives you the conditional expectation of y given x at each value of x. So that, in a sense, is the ideal function for a population, in this case, of y and a single x. So let's talk more about this regression function. It's also defined for a vector x. So if x has got 3 components, for example, it's going to be the conditional expectation of y given the 3 particular instances of the 3 components of x. So if you think about that, let's think of x as being 2-dimensional, because we can think in 3 dimensions. So let's say x lies on the table, 2-dimensional x, and y stands up vertically. So the idea is the same. We've got a whole continuous cloud of y's and x's. We go to a particular point x with 2 coordinates, x1 and x2, and we say, what's a good value for the function at that point? Well, we're just going to go up in the slice and average the y's above that point. And we'll do that at all points in the plane. We said it's the ideal or optimal predictor of y with regard for the function. And what that means is, actually, it's with regard to a loss function. And what it means is that particular choice of the function f of x will minimize the sum of squared errors, right? Which we write in this fashion, again, expected value of y minus g of x over all functions g at each point x, right? So it minimizes the average prediction errors. Now, at each point x, we're going to make mistakes, because if we use this function to predict, which we write in this fashion, again, expected value of y minus g of x over all functions g at each point x, right? So it minimizes the average prediction errors. Now, at each point x, we're going to make mistakes, because we've got a whole continuous cloud of y's and x's. We go to a particular point x with 2 coordinates, x1 and x2, and we say, what's a good value for the function at that point? Well, we're just going to go up in the slice and average the y's above that point. And we'll do that at all points in the plane. We said it's the ideal or optimal predictor of y with regard for the function. And what that means is, actually, it's with regard to a loss function. And what it means is that particular choice of the function f of x will minimize the sum of squared errors, right? Which we write in this fashion, again, expected value, but on average it does well.
哦，懂了。G function mean square irreducible error.
For any estimate f hat of x And that's what we tend to do. We tend to put these little hats on estimators to show that they've been estimated from data. So f hat of x is an estimate of f of x. We can expand the squared prediction error at x into two pieces. There's the irreducible piece, which is just the variance of the errors. And there's the reducible piece, which is the difference between our estimate f hat of x and the true function f of x. Okay? And that's a squared component. So this expected prediction error breaks up into these two pieces. So that's important to bear in mind. So if we want to improve our model, it's this first piece, the reducible piece, that we can improve by maybe changing the way we estimate f of x. Okay, so that's all nice. This is a kind
is also defined for vectors. Distribution.
kind of, as up to now, has been somewhat of a theoretical exercise. Well, how do we estimate the function f? So the problem is we can't carry out this recipe of conditional expectation or conditional averaging exactly, because at any given x in our data set, we might not have many points to average. We might not have any points to average. In the figure, we've got a much smaller data set now, and we've still got the point x equals 4. And if you look there, you'll see carefully that the solid point is one point I put on the plot, the solid green point. There's actually no data points whose x value is exactly 4. So how can we compute the conditional expectation or average? Well, what we can do is relax the idea of at the point x to in a neighborhood of the point x. And so that's what the notation here refers to. N of x, or script n of x, is a neighborhood of points defined in some way around the target point, which is this x equals 4 here, and it keeps the spirit of conditional expectation. It's close to the target point x. And if we make that neighborhood wide enough, we'll have enough points in the neighborhood to average, and we'll use their average to estimate the conditional expectation. So this is called nearest neighbor or local averaging. It's a very clever idea. It's not my idea. It was been invented a long time ago. And of course, you'll move this neighborhood, you'll slide this neighborhood along the x-axis, and as you compute the averages as you slide in along, it'll trace out a curve. So that's actually a very good estimate of the function f. It's not going to be perfect, because the little window has a certain width, and so as we can see here, some points of the true f may be lower and some points higher, but on average it does quite well. So we have a pretty powerful tool here for estimating this conditional expectation. Just relax the definition and compute the nearest neighbor average, and it gives us a fairly flexible way of fitting a function. We'll see in the next section that this doesn't always work, especially as the dimensions get larger, and we'll have to have ways of dealing with that.
就这样。Dimensionality structure.
Okay, here we're going to see situations where our nearest neighbor averaging doesn't work so well, and we're going to have to find ways to deal with that. Nearest neighbor averaging, which is the one we just saw, can be pretty good for small p, small numbers of variables. Here we had just one variable, but small, maybe p less than or equal to 4, and largish n. Right? We want large n so that we have enough points in each neighborhood to average to give us our estimate. Now, this is just one version of a whole class of techniques called smoothers, and we're going to discuss later on in this course much cleverer ways of doing this kind of averaging, such as kernel and spline smoothing. Now, there's a problem though. Nearest neighbor methods can be really lousy when p is large. And the reason has got the name the curse of dimensionality. What it boils down to is that nearest neighbors tend to be far away in high dimensions. So, and that creates a problem. We need to get a reasonable fraction of the n values of yi to average to bring the variance down. So we need to average a number of points in each neighborhood so that our estimate has got a nice, reasonably small variance. And let's suppose we want 10% of the data points to be in each interval. The problem is that 10% neighborhood in high dimensions need no longer be local, so we lose the spirit of estimating the conditional expectation by local averaging. So let's look at a little example of that. In the left panel, we've got values of two variables, x1 and x2, and they're actually uniformly distributed in this little cube with edges -1 to +1, -1 to +1. And we form two 10% neighborhoods in this case. The first neighborhood is just involving the variable x1, ignoring x2. And so that's indicated by the vertical dotted lines. Our target point is at 0. And so we spread out a neighborhood to the left and right until we capture 10% of the data points with respect to the variable x1. And the dotted line indicates the width of the neighborhood. Alternatively, if we want to find a neighborhood in 2 dimensions, we spread out a circle centered at the target point, which is the red dot there, until we've captured 10% of the points. Now notice the radius of the circle in 2 dimensions is much bigger than the radius of the circle in 1 dimension, which is just the width between these two dotted lines. And so to capture 10% of the points in 2 dimensions, we have to go out further and so we're less local than we are in 1 dimension. And so we can take this example further, and on the right-hand plot, I've shown you how far you have to go out in 1, 2, 3, 5, and 10 dimensions. In 10 dimensions. These are different versions of this problem as the dimensions get higher in order to capture a certain fraction of the volume. Okay? And so take, for example, 10% or 0.1 fraction of the volume. So for p equals 1, if the data is uniform, you roughly go out 10% of the distance, right? In 2 dimensions, we saw you went more. Look what happens in 5 dimensions. In 5 dimensions, you have to go out about 0.9 on each coordinate axis to get 10% of the data. That's just about the whole radius of the sphere. And in 10 dimensions, you actually have to break out of the sphere in order to get points in the corner to capture the 10%. So the bottom line here is it's really hard to find near neighborhoods in high dimensions and stay local. If this problem didn't exist, we would use near neighbor averaging as the sole basis for doing estimation. So how do we deal with this? Well, we introduce structure to our models. And so the simplest structural model is a linear model. And so here we have an example of a linear model. We've got p features. It's just got p plus 1 parameters. And it says the function of x, we're going to approximate by a linear function So there's a coefficient on each of the x's and an intercept. So that's one of the simplest structural models. We can estimate the parameters of the model by fitting the model to training data, and we'll be talking more about how you do that. And when we use such a structural model, and of course this structural model is going to avoid the curse of dimensionality because it's not relying on any local properties and nearest neighbor averaging. It's just fitting quite a rigid model to all the data. Now, a linear model is almost never correct, but it often serves as a good approximation and interpretable approximation to the unknown true function f of x. So here's our same little example data set, and we can see in the top plot, a linear model gives a reasonable fit to the data, not perfect. In the bottom plot, we've augmented our linear model, and we've included a quadratic term. So we put in our x, and we put in an x squared as well. And we see that fits the data much better. It's also a linear model, but it's linear in some transformed values of x. And notice now we've put hats on each of the parameters, suggesting they've been estimated, in this case from these training data. These little hats indicate that they've been estimated from the training data. Okay? So those are two parametric models, structured models, that seem to do a good job in this case. Here's a two-dimensional example. Again, seniority.
어려요.
Years of education and income. And this is simulated data, and so the blue surface is actually showing you the true function from which the data was simulated with errors. We can see the errors aren't big. Each of those data points comes from a particular pair of years of education and seniority with some error. And the little line segments in the data points show you the error. Okay? So we can write that as income is a function of education and seniority plus some error. All right? So this is the truth. We actually know this in this case. And here's a linear regression model fit to those simulation data. So, it's an approximation. It captures the important elements of the relationship, but doesn't capture everything. Okay? It's got 3 parameters. Here's a more flexible regression model. We've actually fit this using a technique called thin plate splines, and that's a nice smooth version of a two-dimensional smoother. It's different from nearest neighbor averaging, and it's got some nicer properties. And you can see this does a pretty good job. If we go back to the generating data and the generating surface, this thin plate spline actually captures more of the essence of what's going on there. And for thin plate splines, we're going to talk about them later in chapter 7. There's a tuning parameter that controls how smooth the surface is. Here's an example of a thin plate spline where we basically tune the parameter all the way down to 0, and this surface actually goes through every single data point. In this case, that's overfitting the data. We expect to have some errors because the true function generate data points with errors. So this is known as overfitting. We're overfitting the training data. So this is an example where we've got a family of functions and we've got a way of controlling the complexity. So there's some trade-offs when building models. One trade-off is prediction accuracy versus interpretability. So linear models are easy to interpret. You just got a few parameters. Thin plate splines are not. They give you a whole surface back. And if you get given a surface back in 10 dimensions, it's hard to understand what it's actually telling you. We can have a good fit versus overfit or underfit. So in this previous example, the middle one was a good fit, the linear was slightly underfit, and the last one was overfit. So how do we know when the fit is just right? We need to be able to select amongst those. Parsimony versus black box. Parsimony means having a model that's simpler and can be transmitted with a small number of parameters and explained in a simple fashion and involve maybe a subset of the predictors. And so those models, if they do as well as, say, a black box predictor, like the thin plate spline or somewhat of a black box predictor, we'd prefer the simpler model. Here's a little schematic which shows a variety of the methods that we're going to be discussing in this course, and they're ordered by interpretability and flexibility. And at the top, there are two versions of linear regression, subset selection and lasso, which we'll talk about, that actually even think the linear regression model's too complex and try and reduce it by, and at the top there are two versions of linear regression, subset selection and lasso, which we'll talk about, that actually even think the linear regression model's too complex and try and reduce it by throwing out some of the variables. Linear models and least squares, slightly more flexible, but you lose some interpretability because now all the variables are thrown in. Then we have generalized additive models which allow for transformation in an automatic way of each of the variables. And then at the high flexibility, low interpretability end are bagging, boosting, and support vector machines. We'll discuss all these techniques, but later on in the course.
Okay, so we covered linear regression and we covered nearest neighbor averaging.
And so those models, if they do as well as, say, a black box predictor, like the thin plate spline or somewhat of a black box predictor, we'd prefer the simpler model. Here's a little schematic which shows a variety of the methods that we're going to be discussing in this course, and they're ordered by interpretability and flexibility. And at the top, there are two versions of linear regression, subset selection and lasso, which we'll talk about, that actually even think the linear regression model's too complex and try and reduce it by throwing out some of the variables. Linear models and least squares, slightly more flexible, but you lose some interpretability because now all the variables are thrown in. Then we have generalized additive models which allow for transformations in an automatic way of each of the variables. And then at the high flexibility, low interpretability end are bagging, try and reduce it by throwing out some of the variables. Linear models and least squares, slightly more flexible, but you lose some interpretability because now all the variables are thrown in. Interpretability because now all the variables are thrown in. Interpretability because now all the variables are thrown in.
我写错了吧？哎 ，shit！ 我怎么反应他写错？
Interpretability because now all
这个可以吗？Could you explain? 我怎么说他写错？我怎么反馈 ？Discussion。GoPro 又宕机了。是不是要改正啊？不改正好像没有分数，真的？原来分数要改正。我怎么反馈啊？
Interpretability, because now all the variables are thrown in.
Nuts.
Then we have generalized additive models which allow for transformations in an automatic way of each of the variables. And then at the high flexibility, low interpretability end are bagging, boosting, and support vector
Bagging, boosting.
machines. We'll discuss all these techniques, but later on in the course.
Okay, so we covered linear regression and we covered nearest neighbor averaging, and we talked about places where that's not going to work. And so we've briefly introduced a number of other different methods, and they're all listed on the screen. Different methods that we can use
to solve the problem when the dimension's high and when linearity doesn't work. But we have to choose amongst these methods. And so we need to develop ways of making those choices, and that's what we're going to cover in the next segment.
A hypercube with side.靠腰哦，这也太难了吧！ a proportion of the points in hypercube of dimension 50, in D dimension E 嘛，边长 E in D dimension is defined to be the set of points such that and the boundary of a speed point to be the set of points such that there is a J which link hypercube 到底是什么？ 靠腰哦，猜猜看。In the boundary.哦，好像有个答案哦。0.05 0.95 1 The boundary is a set of points that have at least one dimension.这个还可比到底是什么？这种 volume。Hypercube 应该有个公式才对。想想看。 dimension 50. 计算机。宕机了。Move。怎么就宕机了呢？这 Coursera EDX 宕机了，应该是他们那边的问题。看一下，假设开这个。